This video is going to cover pushdown automata, or PDAs. We're going to go over 4 examples from the textbook. Our first example, we're going to create an NPDA, or non-deterministic pushdown automata, for the following language. This language is a to the n, b to the n, where n is greater than or equal to 0, union with the string a. This language is basically an equal number of a's and equal number of b's put together, where the b's follow the a's. N is greater than or equal to 0 means that we have to include the empty string, and then we also need to include this single string a. The key ideas to creating our NPDA are that we need an equal number of a's and b's. So we're going to use the stack to count the number of a's. And we need to include a singular a in our solution as well. Let's go through this idea and try to build our automata. How about every time we read an A, we put a 1 on the stack? These 1s will act like counters. So every time we see an A, we'll add another 1. So our stack will literally be a count of A's. There will be as many 1s on the stack as there are A's in our input. First, we have to start with our stack start symbol. We're going to use 0 in this example as our stack start symbol. Using this input as example, AABB, we're going to create our automata. So the first thing we have to do is read an A, and then we pop the 0 off the stack. Since we've read an A, we're interested in counting that A. So that means we want to push a 1 onto the stack. But we also want to keep our 0 on the stack. So we've popped our 0 off, we're reading our A. We want to count the A's by putting 1s on the stack. We have to remember to put our 0 back on because the start symbol is essential to knowing when we can accept a language and when we can't. So we put a 1 and a 0 back on the stack, where there's 1 on the stack and we've read 1A. Now we read our next symbol and it happens to be an A. We pop the top off of our stack and it happens to be a 1. Since we read an A, we want to put another 1 on the stack. But remember, we have to put our other 1 that we just popped off back on the stack. We read our next letter and it happens to be a B. We also pop our 1 off the top of the stack. We read a B and we popped a 1. So we're starting the actual counting process. Notice that there are 2 1s on the stack and we had read 2 A's. Now we've read a B and we pop 1 off the stack. We don't want to push anything on the stack, and so then we move to the next letter in the input. So now at this point the stack has a 1 and a 0 on it. We've read 2 A's and 1 B, so we've taken one of the counts off the stack. That is one of the 1s. Now we read our second B and we pop the next 1 off of the stack. We're happy here because we're seeing 1s on the stack and we're reading B's. So we're just counting our B's at this point. We move on to the next input and we don't push anything on the stack. Now we read nothing because our input string is gone, we've consumed it all, and a 0 was popped from the stack. This indicates a final state as we've read an equal number of A's and B's and we just finished the input and popped a 0. This string is in the language. Let's formalize this and actually create our NPDA. Our first step in this particular input string is reading an A, popping a 0, and pushing a 1, 0 on the stack. This here is the term for that. This is how we formalize that. So we read an A, we popped a 0, and then we push a 1 and a 0 on. Where the 0 is pushed first, the 1 is pushed second. So the 1 is at the top of the stack. We also transition to Q1 when we do this. Our second step was reading an A and popping a 1, and then pushing 2 1s on the stack. So again, we read an A, we popped a 1, we pushed 2 1s on the stack. This means we've counted 1 A and 2 A's. And this allows us actually to count 3 A's, 4 A's, 5 A's, and 6 A's, and so on, because we continue going back to Q1 and pushing 2 ones onto the stack. In this particular example, we now read a B. And so we transition to a new state. If we don't transition to a new state, then it would allow us to read an A, B, A, which we don't want to do. So we transition to a new state, Q2. We pop a 1 off of the stack, and we don't push anything onto the stack. We've counted all of our A's now, and now we're counting our B's. Our fourth step was reading our second B and popping a 1 and pushing nothing onto the stack. Again, this allows us to read 2 B's, 3 B's, 4 B's, 5 B's. We just keep going and going and going and ending back at Q2. Now, Q2 is not a final state. Our final step was reading nothing, that is consuming the whole input tape, and then we pop a 0 off the stack and we push nothing back to the stack. This indicates to us that we've consumed our entire input string, and we see the stack start symbol. That is, we don't have anything left to look at on the stack. So we've counted all the A's, and we have exactly the number of A's and B's, and we're done. Now, what are we missing? We're missing a couple of things. The first thing we're missing is our individual A string that's included in this language. So we have to accept just reading an A, popping a 0, and pushing nothing to the stack. So if we read an A and we pop a 0, we can push nothing to the stack and we can be done. But if we read an A and then a B, then we have a dead state and it's not accepted. We're still missing something. We're still missing the fact that you can accept the empty string. So we add one more transition to our final state, which includes the empty string, where we read nothing, we pop a 0, and we push nothing to the stack. This is our final NPDA. It has 4 states, Q0, Q1, Q2, and Q3. Our alphabet includes A and B. Our stack alphabet includes 0 and 1. Our start symbol for the stack is 0, and our final state is Q3. These are our transitions, which are just clearly indicated here. This is an NPDA, non-deterministic, because you may read an A and go to Q1, or you may read an A and go to Q3. Our second example, we're going to create an NPDA for the language where words are in the set A, B star, meaning they're any combination of A's and B's, and the number of A's in W is equal to the number of B's in W. For this language, we need an equal number of A's and B's just like before, but the A's and B's can be in any combination in any order. We can use the stack to count the number of A's and the number of B's. So now instead of using just ones to count A's, we're going to count A's with a stack symbol and we're going to count B's with a stack symbol. A's and B's can be in any order, which makes this different than the last one. Let's go through a way to solve this. Let's use the input tape A, B, B, A as a means of solving this. How about every time we read an A, we put a 0 on the stack, and every time we read a B, we put a 1 on the stack? Let's start with the stack symbol Z. We read our A, and we pop Z off of the stack. We're counting A's with 0s, so we push 0Z on the stack since we read an A. We read a B, and we pop the 0 off the stack. Reading a B and popping a 0 off the stack means we have read an A before, and we're now reading a B. So we can leave the 0 off the stack and not push anything, since we've read exactly one A and one B. Now we read a B and pop the Z off the stack. Remember, we're counting B's with 1. Since we didn't pop a 0 off, we have to push a B counter, that is a 1, so we can make sure that when we read another A, then we can accept. So we push 1Z onto the stack. Now we read an A and pop a 1 from the stack. Reading an A and popping a 1 means that we read a B before and now we're reading an A. So we have an equal number of A's and B's at this point. We push nothing and we read the next character. Now we read nothing and we pop a Z. This indicates that we have read an equal number of A's and B's, and so the string can be accepted. Let's formalize this by actually constructing our NPDA. Let's look at our example ABBA to do this. Our first step was reading an A, popping a Z, and pushing a 0Z on the stack. We transition from Q0, our start state, to Q1 when we do this. Here, remember, we're reading an A, popping a Z, and pushing 0 and Z onto the stack, where Z is pushed first, 0 is pushed second, so 0 is at the top of the stack. Similarly, if our first letter was a B, we would read a B, pop a Z, and push 1Z. Our second step with this particular input tape was reading a B, popping a 0, and pushing nothing. Similarly, if we read an A at this point and we popped a 1, we'd push nothing. Next, on our input tape, we read a B and pop a Z from the stack. This means that we have to push a 1Z back to the stack. This looks a lot like the first transition from Q0 to Q1. So we can either create another transition to another state, or we could realize we're kind of going to run into this a lot, and we could create a loop. In fact, there's no reason we can't loop all the existing transitions back to Q0. This is what we have instead. We can do this because we don't want to accept any of these strings. If we've made all of these transitions, we still have more to do before we accept. These transitions in English simply say A, Z, 0, Z. If I read an A and the stack is empty, count the A. B, Z, 1Z. If I read a B and the stack is empty, count the B. A, 1, lambda. If I read an A and the top of the stack is a 1, then remove the 1 as a B count. B, 0, lambda. If I read a B and the top of the stack is a 0, then remove the 0 as an A count. Now we have to deal with the case where we read 2 A's in a row and 2 B's in a row. If we read an A and we just read an A, then we're going to pop a 0 off the stack, which means we need to put 2 zeros on the stack, which is this here. If we read a B and we just read a B, then we'll pop a 1 off the stack, and then we need to push 2 1s onto the stack. This is the case where we read 2 A's in a row or we read 2 B's in a row. And this is basically it. These are all the things that can happen. We can either read A with an empty stack, we can read B with an empty stack, that's these two. We can read A when we just read a B, we can read B when we just read an A, or we can read an A when we just read an A, or read a B when we just read a B. Now we need to get to this accepting of strings. What condition would facilitate accepting a string? We accept a string when we read nothing and pop a Z, that is the stack start symbol. If we are at the end of the input, that is the input has been consumed by all of the operations above, that means we've read exactly as many A's as B's and we can be done. The book shows that our final transition from Q0 to Q1 is lambda ZZ. That means that you read nothing, you pop a Z, and you push a Z. But what you put back on the stack doesn't matter. You're in a final state, and so you're done. So I didn't put anything back on the stack. This is our final NPDA for this language. We have two states, Q0 and Q1. Our alphabet is A and B. Our stack symbols are 0, 1, and Z. Our initial stack symbol is Z. Our starting stack symbol is Z. And our final state is Q1. Our transitions are listed here, and they're exactly the same as these transitions here. Our third example is a little bit more interesting. Instead of counting A's and B's, we're actually going to do a word and its reverse. So this language includes words and their reverse concatenated together, where a word comes from the set A, B plus, meaning there at least has to be one letter. The key ideas to creating this NPDA is that we're going to have a very similar stack alphabet to our input alphabet. In fact, we're just going to include one additional symbol, which is going to be our stack start symbol. We're going to put W on the stack and pop it off to identify WR, because if we push W in order onto the stack, when we pop it off, it'll come off in reverse order. The non-deterministic nature of NPDAs allows for us to identify the end of W, that is the middle of our word. If we find the middle of W, then we can find the beginning of WR, and then we know when we're actually reversing the word instead of just adding to the word. This will make more sense in a minute. Let's go through an example to figure this out. We're going to use the example ABBA, just like we did before, which is AB backwards, ABBA. And we're going to start with Z as a stack start symbol. We're going to read each letter of the input and push it onto the stack. With each input, we'll check to see if it matches the letter on the top of the stack. If the current letter matches the letter we popped off the stack, then we can take two paths. We can either push the current letter onto the top of the stack, assuming that we're still reading the word, or we can push nothing, assuming we're reading the reverse of the word. So think about it. On the third input letter, B, we have read A and B. So now we've popped a B and we're looking at a B. So we could be in the situation where the word isn't finished, or we could be in the situation where the reverse of the word is starting. So we have two different paths. Let's start this example. We're going to start by reading an A and popping a Z. We've obviously just started because we have a Z, so we want to push AZ onto the stack and continue. Now we read a B and we're popping the A off the stack. Since those two letters do not match, we're going to push B and A back onto the stack. Because we know we haven't started the reverse of the word, because the reverse of the word can only start when the letter on the top of the stack and the letter that we're reading are the same. We push BA back on the stack. Now we read our third letter, which is our second B, and we pop B off the stack. This is when we have two options. Since the input symbol and the symbol on the top of the stack are the same, we have the following two options. Either W is done, it's not done, sorry. Either W is not done, and so this is part of the word, or WR has started, and so this is the beginning of the reverse of the word. We can handle this by taking a non-deterministic transition, that is transitioning to two different states. We'll represent this with two stacks. Stack 1 will assume that W is continuing, and stack 2 will assume that WR has started. For stack 1, if W is continuing, then we're going to push BB onto the stack. For stack 2, if WR has started, we're going to push nothing. Now we read the second A and pop B off stack 1 and A off of stack 2. For stack 1, the only choice is to assume W is still going, as the input symbol doesn't match the popped stack symbol, so we push AB. For stack 2, we've already assumed that we're reading WR, so we're looking for matching letters, which we have, so we push nothing. Now we read nothing and pop A off of stack 1 and Z off of stack 2. The path taken with stack 1 leads to a dead state, where the string is rejected. We're at the end of the string and the stack has stuff on it, so we're not happy. The path taken with stack 2 results in an empty string and the stack start symbol, so we accept. Let's formalize this by actually building our NPDA. Our first step was reading an A, popping a Z, and pushing AZ on the stack. We can stay in Q0 for this. Similarly, if the first character we read is a B, we can push a BZ on the stack. Now we read a B and pop an A from the stack, pushing BA back onto the stack. Similarly, if we read an A and pop a B from the stack, we push AB. Now we get to the interesting part. If we read an input symbol that matches the symbol on the top of the stack, we have two choices. Continue assuming W is not finished, that is, keep pushing onto the stack, or assume WR has started, aka keep popping from the stack. We will include two transitions for this. One stays at Q0, assuming W is still being read. So if we read an A, pop an A, we put two A's back on. If we read a B, pop a B, we put two B's back on. One transitions to Q1, assuming WR is being read. That is, we're already reversing the word. So if we read an A, pop an A, we push nothing. Read a B, pop a B, we push nothing. And now we're in Q1. Q0 continues to process the input as if reading W, that is, pushing onto the stack, and Q1 will process the input as if WR is reading, popping from the stack. So here we have the same transition from Q0 to Q1, just back to Q1, where we continue popping letters off the stack so long as they match. Finally, if we read nothing and pop the stack start symbol, we can accept the string. That is, we've consumed the input. Now the only thing on the stack is the stack start symbol, and we push nothing onto the stack. That means we've read and consumed the entire input. There were an equal number of A's as there were B's. Nope, this is a different example. There was a word that we read, and then we read the reverse of that word, and now we have consumed the entire input string, and we have pushed nothing onto it, and we're done. This is the formal definition of our NPDA. It has three states, Q0, Q1, and Q2. It has an input alphabet of A and B. It has a stack alphabet of A, B, and Z, so very similar. Our start state is Z, and our start input symbol for the stack is Z, and our final state is Q2. These are our transitions. This is where the non-determinism comes into play. So you either assume the word is still being read, so you push the same symbol on twice, or you assume it's the reverse of the word, and so you're popping things and transitioning elsewhere. On to our final example. Our final example is the language of A to the N, B to the 2N. That means there's twice as many B's as there are A's. We also need to include the empty string since N is greater than or equal to 0. At this point, I think you've got the hang of it. So for this, we're gonna basically just do the following. For each A that we see, we can put two stack symbols on the stack, and then for each B, we'll pop one stack symbol. At the end, we'll read nothing and pop the stack start symbol to accept the string. We also need to accept the empty string. So here what we're doing is every time we see an A, we're going to put two A's on the stack. And then when we read a B, we'll pop one of the A's. This allows us to have double the A's that we actually read and then use them as a counter for our B's. Our first step is to accept the empty string. So we're going to make Q0 our start state as well as our final state. So now we transition. If we read nothing, that is the empty string. We pop our Z, our start symbol, off of the stack, and we push nothing. Then we can accept. Our second step is if we actually read something, and we read an A, we're going to pop a Z, and then we're going to push two A's along with the Z onto the stack, transitioning to a non-final state because we haven't read any B's. We repeat this process at Q1, pushing two additional A's onto the stack each time. Once we finally read a B, we have to transition to a new state, because if we transition back to Q1, then it allows B's in the middle to be followed by A's, which we don't want. We transition to a new state, Q2, and we push nothing onto the stack. We read a B, we pop an A, we push nothing. We repeat this process at Q2 until the input string has been fully consumed. Once the input string has been fully consumed, we can transition to a final state, assuming that the stack is also empty, only the start symbol is popped. So we read nothing, we pop the Z, the start symbol, and we push nothing. We can consolidate this so that Q0 is the only final state. There's no problem with doing this because now the stack is empty. There's no valid transition out of Q0 after we transition there from Q2 because the stack is empty. Now, if we were to change this and push Z onto the stack, then we could end up in a really weird place. But because we're pushing nothing onto the stack, then we won't accept words in the language that we won't accept words that are not in the language. That's going to cover all of our examples for Pushdown Automata. Make sure you read the book and go through other examples. But hopefully this was helpful and illuminating in your understanding of Pushdown Automata.